Right. Good morning and welcome to the last Quantum BW colloquium of this year. My name is Philipp Kunst. I am a member of the Fraunhofer IAO quantum computing team, and I will be guiding you through this session today. Quantum BW is a state initiative for quantum activities in Baden-Württemberg, which was kicked off last year, with the goal to combine existing expertise and create an overarching umbrella brand to strengthen existing networks and make them more visible. With this colloquium, we want to foster the scientific exchange on quantum topics by presenting the latest developments in this field and promote the idea of co-development for quantum solutions. Today I have the honor to present our speaker, Professor Enrique Solano. Professor Solano is co-CEO and co-founder of Kipu Quantum, a German quantum computing startup based in Berlin. He has written and contributed to numerous influential papers, has worked in a variety of countries across the globe in various academic and entrepreneurial positions. Today he will talk about useful quantum computing in the NISQ era, in particular about digital analog and digital analog quantum computing paradigms, as well as the possibility of reaching quantum advantages for industry use cases with current quantum computers. There will be a Q&A session after the talk. Feel also free to post questions online if you are joining via the live stream. And without further ado, Professor Solano, the stage is yours.
Thanks a lot, Gib. So, Okay, wonderful. So, yeah, I am glad to be here. I think I have passed the train station of Stuttgart a couple of times, and probably the airport, but for some metaphysical reasons, I got several invitations, I recall, from Professor Jörg Brachtuk and others, and it never happened. You know. Now I'm very happy to be here and to share with you some ideas about the topics that were mentioned in the title and in the abstract. I have been long enough in the quantum community, since 25 years, and very active, so I consider myself as knowing too much also about what happened, how it started, and how it evolved. So my opinion is to be taken in a wider sense, and also my critical opinion about the current trends of quantum computing to be valued in that perspective, right? So quantum computing is not something that appeared 1 or 2 years ago. It's something that exists already for a while, and I have particular allergies to many claims and selling points about it that you will hear today, right? Directly from me. My opinion is quite well known to be rather orthogonal to the mainstream. If my opinion were aligned to the mainstream, I would not be here, by the way. I always educated my students and researchers, telling them, if you go to give a talk, say something that nobody can say in your place. If you are going to repeat what others think, send a postcard. So I am not sending a postcard. I'm here to say things that I hope that you disagree and that you, I'm not saying learning, but at least you will challenge your views. Okay, the first topic about quantum computing, but it's more a general, a personal trace of my character and my view as an artist, as a scientist, as a technologist, and now entrepreneur, is that I don't use the word future almost any time in my life, and much less in quantum computers. So if I work in quantum computer, is to make them useful now or never, right? And that's a challenge that we all should take or leave, right? So the idea of quantum advantage now is something that is very close to me, and I will not give up until it happens, right? So, and by the way, given that they told me 30 to 40 minutes, the colloquium and then Q&A, but I like a lot to be interrupted politely. As I said, don't throw tomatoes, but at least say, oh, I want a question and so on. But I will be sharing with you some views. So just not to to betray the goal and not to miss, because I have too many slides for 30, 40 minutes, I prepared the first ones. And as I was telling some friends, I come from 25 years of academic course. I have been director of many research centers in many countries, published too many papers and so on. But now my slides look very industry level and less technical, but anytime you can ask technical things, of course, right? So first of all, we have prepared this slide to show you how we think. The first statement, I hope it is, some people are shocked when I say this, but it's so obvious, you know, quantum computers have outperformed classical computers since many years and many times, too many times, you know? So when people question that quantum computers have the capacity to outperform classical devices, I'm truly worried about how much educated you are into the history of quantum. You know, and this has happened many times. In fact, recently in one of the meetings of the DLR, I was talking to some colleagues from neutral atoms and told me almost every experiment that we did already outperformed, it's not possible to be simulated. And said, yeah, but why you don't shout it? Because nobody cares about analog quantum simulators or analog quantum. Oh, really? Okay, fine. Then you go to see the recent a Nature paper of Google with the Willow stuff, right, saying, 10 to the 25 years to simulate that. I mean, that's rather boring, at least to people that are long enough in the field. You know, this has happened too many times. In fact, you can even check a paper of Immanuel Bloch with Jens Eisert from 2011. It's a science paper where it is even in the abstract that it is impossible to simulate classically for this and that reason. So that's a statement, right? So now, from this point of view, if you see this plot, when you see classical regime, quantum regime, this region, no quantum advantage because you can use classical computers and solvers. The other extreme is what is called computational quantum advantage, is when nothing can beat these quantum results. And this intermediate place is where I think that we are. And the names matter not so much, really. For example, IBM called it quantum utility last year or this year. There was a debate whether they meant quantum advantage or not. You know, there is a difference also that I belong to the tradition that separate quantum supremacy from quantum advantage. The famous paper of Google, 2019, I think, was the title Quantum Supremacy, and we meant at that time still quantum supremacy for useless, non-industrial, non-commercial solutions, and quantum advantage for the industry. Nowadays, everybody has shot in all directions, and it's very hard to trace, but we still make this difference. So I put computational quantum advantage, and I associate advantage to industry use cases. So, and this commercial quantum advantage, which people also protested when I started to use it, what we mean is very simple, is this transition in which customers or even academic people can say, I prefer to use quantum computers because of A, B, and C, even though there may still be a possibility to solve it classically, be for energetic reasons, or for time reasons, or for price reasons, that you feel this transition. And I claim that we are very close to pass this transition. My prediction is that this area of the break-even point is going to take 6 to 12 months, not more. At least we are working such that it is only 6 to 12 months, and we expect perhaps by 2026 already to be on the other side. Another thing that I wanted to tell you directly is that I think that I come from a theory quantum, right? So I'm not, I think I'm entitled to speak in the name of our community. We have not done our job as theorists in quantum computing, be in quantum algorithms or in whatever. The real heroes of this story are the hardware teams, and in particular commercial quantum hardware that have been boosting in the academia and also in the industry. These people have been truly putting qubit by qubit and fighting against the coherence and against control and so, and that's something that we have to change. This story of saying, I do quantum algorithms that will outperform classical computers, you know when somebody will provide me a fault-tolerant quantum computer that is universal. Come on, guys, that's a banality, right? So more or less is the hardware people are the stupid ones. I am the genius, you know. I have the solutions to everything. You know, it is those guys that cannot provide me. I have everything. I have all the solutions. No. The real challenge is the opposite. Go to the lab to say, what do you have in the lab? And with that hardware, you use your genius and build useful quantum algorithms now. And that's what I have been doing in the last years. and I'm here to share more ideas. So that's more or less what I mean by this transition. Quantum computers have already outperformed classical computers for not very commercial things, a fact since many years. It's trivial to prove even, but anyway, if you want to quote the recent Willow chip, you can also quote. Second, the possibility of extracting usefulness to the industry level for quantum computers now, is it possible? And I invented something that I call the cosmological curse for quantum computers, and it's the fact that the only difference between supremacy for useless and advantage for useful is just that humans said, that's useful, oh, the cosmos forbids that. Oh, that's useless, that's academic, oh, the cosmos allows. So there is no magic, there is no cosmological curse here. It's just a question to say the same hardware that provides quantum supremacy for non-industrial cases can be used for industry-level cases. That's a fact. What's the difference between the two? The creativity of the engineers of quantum algorithms to encode in the same amazing hardware, noisy still, but amazing hardware, the useful cases for commercial reasons. I don't think I'm saying, I have said it so many times that I find it so trivial that sometimes I'm really, really surprised that people disagree with that statement, but I can understand, okay? So these are, as I said, I will skip many slides because of the time, but these are some reasons, many times when we use this commercial quantum advantage, people will start to pay just because the answer is better, the faster time to solution, less energy cost, less computational cost, and so on and so on. And even though it is still a question, I do believe that people will start using quantum computers first because of energy consumption than even for computational quantum advantage. And that's a fact, for example, in particular associated to large language models and generative AI. I don't know if it is true, but I have heard already more than once that Microsoft is even considering or building a small nuclear plant to cool down the GPUs of NVIDIA for ChatGPT and so on. So these are the kind of things that for sure will make a game changer, and people will prefer to use quantum computers just because they use less energy. What I know is that I saw an interview of Sam Altman some weeks ago saying, I don't care that I burn so much energy, because my results are so good that people just have to accept it. Yes?
So you're talking about the energy costs.
Yeah.
Do we have some kind of an idea how much it costs at this current point?
Yeah, sure. So let me give you a very an overkilling answer. Take the Willow, the recent Nature paper. If it is true, if they fail in the 10 to the 25, imagine that it is 10 to the 15, whatever is too much, If the computation of a supercomputer takes 10 to the 25 years, what do you think about the energy consumption of that? See? So if making circuit random sampling for 10 to the 25 years, whatever it is just too much energy. It is longer than the age of the universe, just that you get. So from all points of view, energy consumption is an issue between classical and quantum, and the fact already that ChatGPT is about to start burning even nuclear energy is a sign that quantum computers can perhaps be used for the reason of energy, okay? But there is also time to solution and price and so on and so on. So these are just a few things. Then, I will enter into the more technical things that I offer about digital, but I didn't want to skip what matters, because I like to go directly to the point. We believe that these are three paths to quantum advantage that we are working on. I will mention some technicalities. You may allow me not to be that open on technological secrets. But essentially, we believe that in image classification, in combinatorial optimization, and the simulation of chemistry and materials are paths to quantum advantage now. And what I mean by quantum advantage is, of course, quantum algorithms solving industry-level problems in hardware. And when I say in hardware, I even add commercial hardware, because my colleagues, given that I come from academia, sometimes I am insulted, part of life, but even attacked. Say, why you don't keep collaborating with academic quantum computers? The reason, if I have to queue on IBM or on IonQ for an access, and it's already hard to wait for 5 hours so that my quantum algorithm runs, you can imagine what is to be passing the hand to your friends so that they are convinced, and 3 years later they run one neural experiment. It's just absolutely out of place. My team in Berlin gets desperate when we have to wait 1 hour for a true quantum experiment running one of our algorithms. We get just desperate. Typically, we are moving very soon towards a 24/7 access of commercial quantum computers, and that's the way we use. Imagine that each time you have to send a message on an email, they say, wait 7 hours to send an email. I mean, doesn't work, right? That's the level we are trying to do. So concerning these three topics, I will just directly to the point. We have found something that I have to confess that it is not magic, but we don't understand very well, but it worked. In fact, the paper was accepted last week, or this week, in fact. What we discovered is that there are ways of using data we took realistic data from breast cancer. We used convolutional neural networks to map it on a quantum computer, and we developed what I will explain later, what is called digital analog, but it also works with analog encoding. And we use a true quantum computer, B from neutral atoms of a quantum annealer, to compose, first of all, to reduce the size of the images, and then to estimate the features and to be able to predict. So literally, we took the best data of breast cancer prediction from machine learning, and we compared it with our algorithm. We call it, the names are quite tricky, I'm not good at that commercial thing, but it is digital analog quantum convolutional neural networks for image classification. Every word means what it means, right? But essentially, we discovered a method to encode images through this procedure, and we were able to predict that after testing it, our algorithm in thousands of images, that we could predict a little better breast cancer, for example, but a little better means when the best machine learning did it with 90% of success, we did it 91%. You said, oh, it's not very exciting. That's true, it's not very exciting. If you save 2 more lives, it would be exciting, right? But the real result is that the number of parameters were 3 orders of magnitude less, and that's much, much more meaningful than the 90 to 91%. And this was the first results, and now we are trying to test correctly in different hardware providers such that we can make it happen. This requires or digital analog encoding or analog encoding, and for that I will come back. But as I said, the details of this, you can find it in a paper. The confidential things on how to enter in the true quantum advantage, you may allow me that I can share with you perhaps in private, but this is something that is part of the secrets of a company. The second application about optimization is extremely difficult, and we take it very, very seriously, how to use what people call high-order binary optimization. And also here, this is a discovery for many, and I have to share again, sometimes we feel ourselves like rediscovering the wheel, because, for example, even investors approach us to say, you are advertising too much Hubo cases for optimization. Nobody cares about Hubo. Oh, really? And somebody told me even, go to ChatGPT, you see that Hubo solves nothing. Everything is Kubo. And we had to discover that, in fact, nobody cares about Kubo. In fact, everything is Hubo native. It's just that the classical solvers have, for example, Gurobi cannot solve correctly Hubo, therefore people use Kubo. And the fact that we use Kubo and Kubo and Kubo for decades, then somebody didn't realize that most of the interesting problems in industry that are hard to compute are native Hubo, that are mapped to Kubo because Kubo can be done. I always give the example that harmonic oscillators, as we studied in the schools and universities, very likely do not exist in nature. But we find them everywhere in the literature. Why? Because we understand them, this is easy to solve, and we can compute them even analytically, right? We have found even harmonic oscillators in the quantization of light, if you want. I'm a quantum optician, so I'm also an expert on that, And it's just because it's a natural basis that helps us. With Kubo and Hubo, it happens the same. If you go to ChatGPT, I can send you to whoever you want, appears 25 items of the most important problems in finance, biology, chemistry, and everything that are native. And if you attack the problem of high-order optimization, it's much, much simpler than Kubo. And that's what we did. And this is a result that happened. I think I have it here, the result. We ran it in the most advanced IBM Heron First chip of 156 qubits, and we ran a Hubo native problem, in this case only associated to a Hamiltonian that is 3 local But internally now, I can share this openly. We are already on the regime of quantum advantage for 4 local and 5 local. And if you want to know why 4 local and 5 local are important or not, you may want to know that the Nobel Prize given this year for example, protein folding, the problem is, if you map it into this kind of optimization, is a 5 local Hugo native problem that would compete with the classical machine learners. Also, if you belong to these people saying machine learning destroyed quantum computers for protein folding, perhaps you should also hear that it is not true. Because for using machine learning, you need training algorithms. And for training algorithms, you need plenty of data. So when we say quantum computers for protein folding, we mean for designing or identifying structures of molecules that have never been built, probably. Therefore, there is no data. So you can have the best classical machine learning tool, and if there is no data, there is no prediction, right? So in this case, protein folding 5 local is associated to this. You want another use case, dynamic portfolio optimization. If you have not heard, check. So there are plenty of problems. So most of the interesting problems have optimization of this class, and we have solved it on the 156 qubit. Why I say it is a hard cookie? Because classical solvers for optimizations are amazing. So we are since weeks, in private and in calm, days and nights. Some of our guys, I have to send them to sleep because they are obsessed with that. We are trying to beat Gurobi, simulated annealing, Ciplex, DMRG, tensor networks. Sometimes we beat one, we don't beat the other. Sometimes we beat the other, we don't beat the one. And it's a very, very hard job to try to show how this chip of IBM of 156 qubits with our encoding for optimization can produce something close to quantum advantage. I will explain in some minutes how to do that, because this is public, this is in papers. But I just wanted to tell you what is the strategy. Why me as a person and it's a research center, so I feel me bad speaking about my company. I would like to be more intellectual, let's say. But let's say the way me, as a scientist, as a technologist, see the advances of quantum computing on the quantum advantage now, as I said, has a very well-defined strategy. There is, of course, some emotional gut feeling and metaphysical vision. Everything that matters in science has to do with inductive thinking, not with deductive thinking. I don't know how many young people are here. When you read a paper, it is a deductive description, right? That's never the way you invent things. So you invent things, true important things, in an inductive manner, and you present them in a deductive manner. But most of the vision of Kipu is inductive, in the sense that we have to guess or to have this zeitgeist of what is happening in the world today. And I can tell you that the reason why we have decided to make the face-to-face of quantum versus classical now, as I put in one of the first slides, is very simple as a strategy. And I hope you appreciate it, even if you may disagree. Only the people that accept the challenge today means today's Thursday, right? 19th December 2024, to say, I run algorithms, industry level, in the hardware, and I try to reach as far as I can, trying to beat, or at least to compete with the classical solvers. You said, yeah, but that's a lost cause. You may fail. You may fail by just 1%, and then what do you do with that? The solution is fault-tolerant quantum computing in 200 years. That's my prediction. 200 years to be when I am optimistic. When I'm pessimistic is after the big crunch. And in fact, my correct prediction is that nobody will need that, because we will solve many important. Why you would complicate with that if you can solve it before? Right? And so, what is the secret or the vision here? What I said at the beginning, that only the people that accept the fight face to face, sword with sword, of algorithms running in hardware trying to compete with the classical, in 3 to 6 months, if you follow the roadmap of IBM, D-Wave, Google, IonQ, Quantinuum, Pascal, and Quera, in my opinion, the 7 leading companies in different technologies, it is the hardware improvement that will put you on the quantum advantage, on the consolidated quantum. It's not the algorithm. But if you play cheap algorithms, universal algorithms with 5, 10 qubits for the fault tolerance of the far future, the efforts of the hardware people, that is really amazing, is void of content. The only way to praise the effort of the hardware companies that are truly advancing the technology is by trying to use them the way they are now, face to face with the classical algorithms, such that each next step in the hardware will make the advance by itself. And given that we are in these 3 problems I was mentioning, there sometimes beating classical, sometimes losing, is that we just have to wait 3 to 6 months. The next chip comes, Flamingo structure, 3 to 7 Heron Fez, D-Wave improving the fast regime with the advantage 1,200 qubits with a more coherence, IonQ, Quera doing this and that, and your algorithms will reach the level of quantum advantage. So the consolidation of quantum advantage will happen by hardware, not by algorithms. But only the algorithms that try to compete today on the quantum computer versus classical would have a chance to make it. And that's more or less the vision. So we are not very naive here, we are very pragmatic. And I do believe, even though the hardware roadmaps change every 3 months, because these people are truly working on quantum computing, not on mathematics or theorems of quantum speed up, then I mean, even if they fail somehow, quantum advantage will happen along the next year for sure, yes.
I was just wondering about this particular slide. So these simulations are done on all 3 different lattices?
Yeah, I will mention this now. It's just this is the announcements or the statement. I wanted that you hear things that you are not used to hear, okay? And then we can discuss and I can answer technically questions. So these are more so this was my talk. I just wanted to tackle exactly what I said. So these are the 3 things that I offer in the abstract, and it is how I see. As I said, I want to keep my company out of this discussion because it's not an issue of selling things, but of telling you that there is a chance to make it happen now. We see like these three, I call it quantum computing paradigms: the purely digital, the purely analog, and the digital analog. Okay. On the purely digital, I tell you also openly my view. This is the hardest one. Even though if you say to anybody what is quantum computing, they speak about digital 1 and 2 qubit gate, but that's the hardest one. The fact that it's so easy to think and so accessible doesn't mean that it is simple to scale. And I would never call mistake, because I consider, in the same way that I was very critical with D-Wave because of the quantumness, and I have been critical with Zapata computing, I have a total admiration. I think both companies on hardware and on software would be in any book of the history of quantum computing. These 2 companies will be there because they really contributed. As you know, Zapata computing closed this year, which is a pity. I mean, I know everyone, by the way, our friends, brilliant people. But what was their problem? Essentially, that they started in a time where, for example, IBM had 5 qubits accessible in the cloud, or in the labs there were 5, 10 qubits. And then they invented something wonderful that is called variational quantum algorithms. And what was the goal, if you think it carefully? I prefer not to mention names because these are great friends. In fact, you may be surprised that the first article on variational quantum algorithms has my name as last author with Alan Aspurgusi, but it is not cited as the other one. And it was for trapped ions and for chemistry. But variational quantum algorithms had as a goal to put more weight on the classical part than on the quantum. Why? Because the quantum was very small. We had just a few qubits, and that was amazing. That was necessary. It is because of that the community survived until now. What happened? That if you get too excited about revenue that is not substantial, that is not quantum advantage level, your customers, your readers abandon. And everybody became expert in variational quantum algorithms until we discovered that they are barren plateaus and a lot of problems, and that at a certain point, if you want to use variational quantum methods today with 20 or 30 qubits, it could be that the classical effort is you may need a supercomputer or a quantum computer to solve the classical part for the quantum. So at the end, it's a field that is now questioned. I know that some people say it will be back, but this was more or less the history, trying to do digital. On the analog part, on the opposite side, with optical lattices, that is very successful, many people said, that's fantastic. And as I said, many colleagues, if you ask all the leaders of optical lattices and analog quantum computers, they would tell you we reach supremacy every day. That's not a problem. But it is known to be not universal. Digital universal, analog not universal. The problem of analog is not that they cannot be universal. The problem is that the specific purpose applications of the analog quantum computers are not industry level. You know, for example, you can solve the simulation of a spin model. Yeah, but nobody pays for that. Or I can make an optimization, but you know, in fact, you can see the company Quera last year have a Nature paper with 289 qubits in an analog device that reached the point of saying it is an optimization problem. But then when I opened the paper, I went directly and said, where quantum advantage? And there is a moment where they said, sorry, this is very easy to do it classical, you know. So people say, okay, fine, we cannot. So the problem of analog quantum computers is not the lack of universality. It's the fact that by bad luck, by this what I call the cosmological curse, somehow comes a cosmological force and said, if you use 300 qubits and you use atoms and lasers, sorry, nobody will pay for that. You say, man. So even if you reach quantum advantage for an academic problem, you know, people will not pay for that. This is disregarded. And that's the problem of analog quantum computing, you know. But essentially, then where is the point? If the point, at least the way I see it, that instead of running and abandoning analog quantum computing, what we are doing now, what I am doing now, is trying to say, I go to the regimes of analog quantum computing where they claim supremacy, that means outperforming classical computers for useless problems, and I try to use my creativity and my talent to encode there some problem of a certain level of usefulness, okay? Of course, there are ways of abandoning that, and you have companies saying, instead of using analog, I built error-corrected qubits, and so on and so on. Fine. But that's an interesting discussion on how to cope with that. And then the digital analog that we are also working on, you know, I consider myself one of the pioneers on digital analog quantum computing. I know that I can be contested very easily, but I think I have written like 30 papers, and there are many experiments proving that digital analog quantum computing works. But when I invented that, was to compensate the problems of digital and analog. So digital is meant to be universal, but extremely greedy algorithms. Analog is meant to be specific, but the problems that are specific are not useful for the industry. You know, and then with digital analog, what I wanted to be is to be pragmatic, to say, to go and to praise the value of the hardware teams that are building with a lot of effort, qubit by qubit. And then we discovered that with digital analog, you can make it. In this moment, again, I cannot disclose this, but we have algorithms that if somebody provides us digital analog access to a hardware, we can reach quantum advantage for industry-level optimization problems and simulations in a very easy manner. Because digital analog is nothing else than using multi-qubit systems, right, or operations combined with digital, such that the circuit depth of the algorithm will be very narrow. And we are working heavily on that also to make it. So essentially, the way we do digital is different, the way we do analog is different, and the way we do digital analog is different. If somebody questions that digital analog has any hope, you can check also another Nature paper of Google, I think it is last year, where they use, if I'm not wrong, 69 qubits in the previous chip. It was the second generation of the Sycamore, you know, and they use 69 qubits with digital analog encoding to reach a regime for topological things. I disagree with the Google vision. They claim that there is nothing industry level, or it has to be academic. I fully disagree with their vision, right? But they claim that they were able to, no, it's in a paper, digital analog with 69 qubits. So what they did with those 69 qubits is impossible to do with digital quantum computing, because the circuit depth will exceed by far the coherence time of the qubits, right? And also the USTC group, led by Zhang Weipan, also had a paper with, I think, 61 qubits for quantum machine learning, showing that digital analog is alive and could be still a paradigm to boost, okay? So now let me tell you how we do, what is the novelty that I can share with you of making digital. And that's also a message for your creativity, you know? When we said, I am working on digital quantum algorithm, many people said, okay, QAOA and what else? No, we never use QAOA. Never, ever. No. In fact, when we make our plots with this method that I will explain you now of our digital quantum algorithms, and we benchmark, our results are here, simulated annealing is close, TMRG is there, tensor network, QAOA doesn't appear in the plot. I have to make an A3 paper to put QAOA. Is that bad, or it's that easy to beat. Even though it's part of the history and it has to be used constantly, there are ways of improving it, but we don't believe it. And the first goal that we imposed ourselves is that not to make the same, it's not a mistake, as I said, but it's a historical observation, to rely too much on the classical part. So essentially what I will explain you now, it is called digitized counterdiabatic quantum computing that we invented. Is a purely quantum algorithm, and to our knowledge is the best way to compress digital algorithms to almost a minimal effort. And here I will tell you the technical details, and I hope you can ask also if you don't understand. But instead of taking, for example, Shor's algorithm, say I make factorization, Shor algorithm, and then I said, I discovered a trick how to reduce this control node with this Hadamard gate, and so on and so on. The typical way to do quantum computing today, so to pick standard algorithms and to try to tweak to improve. That's not going to work, unfortunately. And again, I cannot guess how wide and interdisciplinary is our audience, but I will repeat things that are so evident and obvious, but that in my career it has cost me even publicly some shameful attacks when I said so obvious things like Hadamard gates do not exist in the hardware, control nodes do not exist in the hardware. They are not native. Therefore, whatever you compute with Hadamard gates and control nodes are just not useful, are not efficient, and not relevant if your goal is to reach quantum advantage. If your goal is just to play around, fine. If your goal is to use the hardware, the front ends of things, enjoy it. But if you want to reach quantum advantage now, the only chance you have is to use native operations, to be hardware specific, and to abandon this fantasy of the hardware agnosticity, which is cool for educational purposes, but it's not for making technology in the next 10 to 20 years, in my personal opinion. Okay, so I repeat, Hadamard and control nodes do not exist. Are composed operations, therefore inefficient. If you want to build algorithms. So the way we did it is to say, it's very weird the way we did it. We said, adiabatic quantum computers are universal. It's a statement. The answer is yes, it was proven. Second, adiabatic quantum computers can be built. You can build some models. Third, why we don't see adiabatic quantum computers all over the planet? And the answer is very painful, because it was proven that the gap between the energy levels, starts to decrease and to be very, very, very small when you put more qubits. And if you put more qubits and the gap is reduced, this means that the adiabatic time is extremely long. And this is so long that it exceeds by far the coherence time of the qubits. So this is science, this is physics. It's not mathematical computer science, this is the fact. A universal model of quantum computing can be tested in the lab, yes. Can it become a technology? No. Why? Because if you want to reach quantum advantage, you need more than at least 60, 65 qubits for general problems like labs problems, for example. And the more qubits you put, the gap is reduced. If the gap is reduced, the adiabatic time grows. And the coherence time of the qubits is the most difficult parameter to improve. If you check from all the parameters of hardware or quantum computers, which is the parameter that improves in a very, very slow manner, is coherence time of the qubits. Therefore, adiabatic quantum computers are not ubiquitous in the technology, okay? But it's a beautiful concept, and we took it, Then, what we did is to say, is it possible, because of the long adiabatic time, to make it faster? And we discovered that there are some fields, one of them called shortcuts to adiabaticity, that was invented by many great friends, that are working with us now. Adolfo del Campo, Xi Chen, and many others, and it's a very successful topic, but we don't like the name shortcuts to adiabaticity, and we started to use a more traditional name that was called counterdiabatic quantum dynamics. And this field that exists in the 90s, more or less, has as a certain goal something very cool. Said, can I modify the Hamiltonian of an adiabatic quantum evolution such that it accelerates while preserving the energy, the ground state, and the result of the energy? So, meaning you induce a non-adiabatic regime, but you preserve the goal of having the ground state. And the answer was yes, but it was a very funny community, very coming from my community of theorists, you know. These people publish plenty of papers in all wonderful journals, but, you know, the modification of the Hamiltonian needed, you know what information? The full diagonalization of the whole Hamiltonian for any time t. So literally, for accelerating theoretically a dynamics, you need to know everything, the present and the future of the dynamics. And of course it works, you know, and people show it, and there were experiments. But do you think it can be useful for a technology? So more or less is for accelerating something, you have to know everything, including the solution. That didn't sound fantastic, you know. And I told my friends, guys, let us do it for a 2-qubit. Let us do a 2-qubit gate with counter-adiabatic dynamics. But you needed to know too much. And as you know, the fundamental aspect of a gate, the difference of a unitary operation and a wave function, is that the unitary operation acts on any wave function without knowing what it is. Right? That's the essence of a gate. And in this case, you needed to know everything, so it was not possible. So what we discovered is that very recent is like 4 years ago, there were some works, you can see people in Germany, who discovered that you don't need to add all the information, that you can put partial information and the acceleration still happen. And this is what people called nested commutator ansatz. So there are many ways, or perturbation theory if you want, kind of, but there are ways in accelerating the adiabatic dynamics without adding all the information that I requested. And that was the origin of our effort. So literally we started by saying, adiabatic quantum computing is universal? Yes. What is my industry problem? It is optimization. Then I take my optimization problem and I encode it in the ground state of an adiabatic quantum computer. And then you would say, raise the hand. But you said that this cannot work. Yes, because we don't build it. We don't request hardware. Then you said, now comes Kike, everybody calls him Kike, and accelerates this with counter-adiabatic dynamics, but not all the information, just partial, the minimal number of terms such that it accelerates. Yeah, but this, you modify the Hamiltonian, yes. So this Hamiltonian is easy to build. No, it is worse. If adiabatic specific purpose Hamiltonians were hard to build, now a counter-adiabatic is even worse. Oh, wonderful technology, right? Then how to solve that? And then we discovered like 4 or 5 years ago that once we reach that, we digitize back to 1 and 2 qubit gate. So it is universal adiabatic quantum computing, encoding the industry level use case, accelerating by minimal effort with counter-adiabatic driving, and then digitizing back. You know what we discovered? You know, it is something very, very shocking to us. In fact, my PhD student, I was working in Shanghai, I was the director of a research center in quantum artificial intelligence, and my PhD student, who is now head of innovation and the most brilliant person on earth, you know, came to my office and said, I found this. I said, okay, fine, it works. And you digitize back, wonderful. And then I said, apply it to factorization. Then he went, applied to factorization, came back, and I said, how is the circuit depth in comparison to Shor algorithm? He went back, came back. It is shorter, the algorithm. And I said, okay, go and change it, it's wrong. Because Shor algorithm has been proven to have the most compact quantum speed up, everything, you know, is the paradigm. In fact, Nobel Prize candidate because this is this. It is because of Shor's algorithm that we are here also, right, among other things. So it cannot be that our algorithm factorizes in, after 2-3 verifications where I had to participate, we confirm. And now we know that so you give me any chip, any quantum computer, hardware, you know, of any size, you just tell me the specs, and then you factorize the best you can with Shor algorithm, and we can do it always shorter and always better for any size and any connectivity. Is there anything wrong with Shor algorithm? No, it was just a computer science result. And ours is physical, scientific, technological, and hardware-based. You know? So that's the moral of the story. Hardware-specific things can give you bored now and will always be like that. You know? When people question the hardware-specific approach that we follow, I'm surprised that you still use GPUs, analog devices. You know, so parallel computing is not really sequential in digital, right? GPUs are not very, very digital sometimes, right? So we have always lived in digital and analog at the same time, since always, and it will always be like that, in classical and in quantum. Right? So here, we discovered that for a specific purpose, you can do it, and that's what we called digitized counter-adiabatic quantum computing. Now, I hope that it's a horrible name, I don't like it, that you understand. Universal problem, universal quantum computer, encoding at industry level, accelerating with minimal effort, digitizing back. You see, digitized counter-adiabatic quantum computing. Now, I can tell you now, this is a statement. Everything since 5 years, and we have applied to hundreds of cases, every use case for academia or for industry that you do with this technique produces shorter circuit depths of quantum matter. Everything. We have not found a single counterexample. You have the right, as scientists, to tell me, explain me why and how. I am sorry to tell you that I can only give you the intuition of why. We have not proved that this is a universal trace, and I forbid my team to try to prove it. We are trying to convince some colleagues why. Because we are not here to prove theorems. We are here to make quantum computers useful. You have to be very focused for that, obsessed with the focus. But the intuition is very beautiful. Is that it was also proven, not only that adiabatic quantum computing is universal, but it was proven that the computational complexity of adiabatic quantum computing is equivalent to the computational complexity of digital quantum. This was proven many years ago, right? So we have found a heuristic relation that when you accelerate the adiabatic quantum computing, it maps into reducing the circuit depth of the digital. It is not, if you try whatever, you say, no, that's not true. But there is always a new mapping or a new encoding that can make it true. And that's something that really troubles us from an intellectual point of view. We are happy with the technological result, but nobody has proved that what I just said is correct always. But we have evidence of 5 years applying to whatever, that we can map. So let's say that accelerating the adiabatic dynamics is equivalent to accelerating the digital, okay? And just to use my 5 last minutes, I passed on the recommended time. I just wanted to say something about the digital analog, right? So so anyway, any question about this digitized counter-adiabatic? You got the point, right? So to go this, yeah.
What I'm not able to understand is that even if you increase the problem size, your Hamiltonian landscape will become that much more complicated, and by adding the counter-adiabatic terms, your gate depth will go so much more higher. And
that's the contradiction. That's exactly what you said. So,
but I don't think we are gaining anything.
That's the point. So as I said, we have plenty of papers already. If you check all our papers, you will be surprised. So the reduction in the circuit depth oscillates between 10 to 100 times. Yes.
But how can you reduce the circuit depth? For example, if your Hamiltonian has, for example, terms that go beyond two-body that are not efficient to implement on the hardware. This further makes this task more difficult, so I'm quite surprised that.
That's the point. But I get your point, but you have to be careful. Your statement has a little flaw. If you have k local terms, k larger than 2, the problem to be trotterizing and using Jordan-Wigner or whatever is the same, right? So for any digital. So any digital algorithm suffer mapping k local terms to 1 and 2 qubit gates, anyone. What I claimed is that ours, when you turn into 1 and 2 qubit gates, is shorter than any other. But the problem...
Introducing additional counter-adiabatic Hamiltonians to make the number of gates that you have per time-step iteration even larger, so how can it be that you compress it in this way? I'd rather see it.
I kindly invite you to read our papers, but that's a fact. There are many methods.
Can you go back to the slide where you reference the papers?
Yeah, let me finish with the digital analog and then we enter in the Q&A. So for the digital analog, I just wanted to tell you that's exactly what you said is our surprise. It just works, and I just presented you the intuition of why it may work always, but it works always, okay? But we go there, and I will tell you more or less also what are the tricks behind. But on the digital analog, I also wanted to tell you
that was is an important thing. Digital operations are like this. Single qubit and 2 qubit rotations, and people call analog. And this is a problem of name. The difference between multi-qubit gates and analog blocks, typically for us, is that multi-qubit gates are time-independent local unitaries acting on n qubits, and analog blocks is more like a quantum simulation with a continuous parameter time acting on many qubits. Yeah, but it's a question of name. But if you combine both, these analog blocks for arbitrary times and local qubit rotations or digital gates, we proved in many instances that you can compress and you can make more profit of the hardware. Now, when I started working on that, like in 2010 and so, I'm a dinosaur for some of you, right? We were very successful because we were doing science. We was a cool one. No? But then came, of course, the critic saying it's not universal, therefore rubbish. Then, I have my pride, and I went to my team and said, guys, does it matter? No, it doesn't matter. Shall we prove it that it's universal? And yeah, we have a paper, I think 2020, where the title is Digital Analog Quantum Computation. It's a horrible paper full of math where we prove that it is universal. So if you give me, we use, let's say, any quantum computer with nearest neighbor coupling, and we took this as the analog block, and we proved that you can always build anything for fermions, bosons, spins, whatever, right? So that it is universal. But the problem is not that it is universal. The problem is that it compresses. And also this is something that I was very surprised. There is a company called IQM. Most of the people that wrote that paper I hired because I was the CEO of IQM Germany. But it turns out that they dared to publish a paper where they prove, apparently, that digital analog almost never works. Prefer not to say who was the referee or one of the referees, but this is true. If you just apply blind analog multi-qubit gates and digital to save something, it doesn't work in general. You have to engineer it. One trivial example is if I give you a multi-qubit gate of 10 qubits and I tell you, build me a 2-qubit gate, it doesn't work. So from that point of view, it needs some effort, okay? No, I'm just finishing. So that's more or less the idea. So digital analog is a way of compressing. It works. It is fantastic, but it is not just an easy cookie. You have to engineer it in such a way that it is meaningful. You have to choose the academic or industry use case, you have to choose the hardware, and you have to choose the encoding, and at the end you're similar to what I said about the digital counter-diabatic quantum computing. It's not a direct thing because of the arguments you gave, right? You are complicating more the Hamiltonian, and now you digitize and you open this, the evolution operator, how can it be that you can reduce? In the digital analog is similar. It's obvious that if I give you a 10 qubit, a multi-qubit gate, and I tell you, make me a 1-qubit gate, it's totally inefficient, right? So it is the composition where is the trick and the method and the gate. So yeah, so I want to stop here. The general message for you is quantum computers in hardware have outperformed classical computers. There is no cosmological curse forbidding humans to encode in the same hardware useful cases. It's just a question of creativity and of accepting the challenge. And the last message, only the people, groups, and teams and companies that are trying to make it happen today will consolidate it in 3 to 6 months with the next generation of chips coming from any commercial quantum computer. That's the general message I wanted to share, and why I do believe that 2025 will be not only the United Nations Year of Quantum Technology, but a true possibility of seeing quantum computers making things useful, which would create an edge. And of course, later will come error correction, later will come fault tolerance. I'm not discarding that. The point is that I was not born with the sense that I work for the posterity. I'm very sorry for those that have this fantasy. I don't work for the posterity. I want for making things successful now. And that's the challenge we took. We think we will make it, but of course people can disagree. So thanks a lot.
Right, thank you very much for the talk. With that, we enter the Q&A session. There has been no questions online yet, but feel free to post them so we can address them. We already had some questions in the audience already, and I guess there may be some more. Is he nodding? Yeah, who would like to start? No.
Finally, when you mentioned that you, after that, adding the tunnel speed up, well, counter-adiabatic speed up, right, you decompose it back into the circuit, right? How complex is it for the classical computer, right? Because it's known to be in general that circuit tailoring is not very easy task yet, and be hard as it is. And so how hard is it for your case?
Yeah, so I mean, you remind me questions of investors, no? That said, okay, you found a cool trick, right? But I don't care is your cool trick if you don't prove me that that it can be done automatically in the server, right, or in your product, right? Because if it is human, each time that you want to do the trick, let's say, you have to have 3 brilliant people trying, playing, then it doesn't work. It's a cool, you make a cool paper, but you don't make a cool technology. So technology is more associated to reproducibility and how trustful it is. And we have been working heavily on that. So as I said, what I have explained today is just the general science around, but the making is quite tricky. So we don't use, for example, error mitigation at all, but we use plenty of inbuilt structures for reduction. But the main, just to give you an idea, we have papers, portfolio optimization, protein folding, chemistry, logistics, job scheduling, factorization, all of them, and publicly we said this is the shortest circuit depth ever for this problem under these conditions. Nobody has dared even to contest that. So I take it like yes, you're right? But in each paper you will find specificities, so methods that adapt to that problem. And then internally, because I also work in a company, this has to be systematic. And this part is the more tricky one. Of course, when you make it systematic and reproducible for a technology, you have to relax so we don't get the best solutions there. Because when you want reproducibility, you have to give up on the best. The best will be done by people, but that's not the way technology works. But we can discuss later, and I can tell you more details on how to make it happen. But as I said, all those examples, as I said, are papers published, and you can see the algorithms and how it happens. So.
There was another question in the back?
Yeah, can you go to the slide where you reference the papers? Where you say that you have those surprises that also surprised me.
I think it is this one.
That's the reference.
No. It must have been before, I guess, a few slides back.
It was there you had the chotorized circuit.
The
23, slide 23.
Wow. 23 is this one.
This one?
Yeah, you mentioned something. So our argument was that you have terms that go beyond to local. So if you want to do them on hardware, your transpilation will increase the depth of your circuit. And then if you introduce this called adiabatic Hamiltonian, that is as even worse. And then your statement is that for you, to a surprise, still you have a circuit compression. So I'm wondering how this can even happen and why you don't have these issues. Because for us, even implementing short depth circuits and small qubit number circuits.
So I will answer you in a very pedagogical manner. It is in a very.
Even if you start with a 10 qubit problem and it bursts, then you go to a 12 qubit problem, like you increase the basis set of some molecular Hamiltonian, everything breaks down.
That's right.
So if you talk about 60 qubits, 100 qubits, it's
that's right. So I will give you a pedagogical answer. If I make a series 1 plus 2 plus 3 plus 4 until n, each time is heavier, right? But if I have a series 1 plus 2 plus 3 minus 3 plus 4 minus 4 plus 5 minus 5, it is simpler, right? So the same thing happens with the unitary version and digitization of a more complicated Hamiltonian. The digitization gets simpler. Because it's not because a series is longer that it's more complicated to calculate. So that's what happens here, effectively. No? As I said, we have not a proof, a mathematical proof that it will always be possible. But now I am telling you about hundreds of algorithms from 5 to 156 qubits where there is not a single counterexample. So I kindly invite you to disprove it or to demonstrate it, but that's what we have observed. But as I said, the reason is that when you make the expansion, many things cancel. So let's say the algebra is reduced. And that's what my intuition is, that accelerating an adiabatic process, given that the computational complexity is equivalent to the digital, has to be mapped somehow in a reduced circuit depth. That's the intuition. Now the proof I don't have. It's only heuristics. And as you know, in computation, heuristics matter a lot, right?
So are you talking about terms that cancel out in the nested commutator expansion of the gauge?
Exactly. When you digitized, suddenly the things get reduced, effectively.
Okay.
But as I said, check the papers, because in the papers
you don't need every term to
exactly. And there are also, I invite you to check something.
The more you take, the deeper your
exactly. So
circuit gets. So
check the topic impulse regime, for example, of quantum algorithms. It's not, we didn't invent it, but also impulse regime has a very, very cool result where you disregard many terms of the Hamiltonian and the algorithms get simpler. Also, we find such level of impulse regimes where even again, I will shock you a little bit, but there are cases where the original Hamiltonian can be neglected fully. You know why? Because in the nested commutator of the counteradiabatic term at minimal level, there is a convolution that involves some terms of the original Hamiltonian, but the original Hamiltonian disappears sometimes completely. You see, because of this, what I'm telling you. So you are right. It's not by making the Hamiltonian more complex that the circuit is reduced. It's that by making modifications that effectively may reduce also the analog part. And as I said, check impulse. We have a paper for portfolio optimization. In the title, I think, is the impulse regime. And in the impulse regime, you can show that you can neglect the original Hamiltonian, and the original Hamiltonian of the problem is only at second order involved in the nested commutator of a commutator. So there are many, many results of that kind that come back to the intuition. Why? Why we have not found a counterexample? And the conclusion is that given that the computational complexity has to be equivalent, accelerating has to mean something in the digital, and apparently it is reduction in the circuit. But we have a meeting now later also that we can.
One last question on that side, I think.
So are you effectively saying that your circuit depth stays constant for larger system sizes?
For
larger systems?
No, not at all. Please, that's a heresy. Not at all. The algorithm, the circuit depth always gets longer. I'm just saying that if you use digitized counteradiabatic quantum computing or algorithm, it will be smaller than any competitor, standard competitor. If you say QAOA, if you say Shora algorithm, you have to refer to that. But at the same time, more qubits and size of the problem implies longer and longer. Just to give you an example, we have the record of 156. This is the largest Hoover optimization ever done by human beings in the largest quantum computer ever. We don't have more. But we know that there will be a number of qubits where our algorithm will die because the coherence sum of the qubits is the same. That's the problem. That's why for those cases, we have other solutions. But that's what I said very frankly. Our digital methods have a dead point. And who gives us the dead moment is the coherence sum of the qubits. I mean, this is something that you cannot change. Everything that you predict beyond the coherence sum of the qubits is fiction, Formally, it is you can call it scientific, but you could not call it technological. It's not non-technological. And we only work in things that can happen in the lab. That's our obsession. I'm not saying it is the correct thing or not. I'm just telling you that we don't propose anything that cannot run in hardware today. And of course, you tell me in 3 months there is a new hardware. We go there and exploit. But what you said, it's not true. So we don't have fixed steps.
So do you have some heuristic scaling for?
Yes, we have. In fact, in one of our previous original papers, we have a prediction. We have studied the scaling of this method that it scales polynomially, and we have evidence now also of a new scale. So we have estimations of scaling. But as I said, we take the scaling more to trying to convince the others, because given that we are a company, what matters is that the customer sees the problem solved in a hardware. And I always tell my colleagues, Scott Aronson, who is one of our intellectual enemies, I always told him, your quantum speed up and scaling, when you go to the hardware and you have n qubits, n is not variable, you just have one chip. You have to solve the problem in that chip, whether it is scalable, speed up, or it's a beautiful mathematics. A given chip is not scalable by definition, and an algorithm. So for us, what matters is give me the hardware, give me the problem. I tell you how to host there the maximal algorithm. That's all that we do. That's our approach. It's not the only approach. If people want to estimate when the speed up will cross, I will say something to finish. Very tough, but I am not here, as I said, to say simple things. Philosophy, mathematical physics, science, technology, product, business. We are trying to transform science into technology to create a product. That's where you find. Error correction is today in physics. Fault tolerant, mathematical physics. Universal quantum computing, philosophy. That's what I think. I do science transform into technology to create a product that I can sell. That's what we do. The Willow, the paper of Google, as beautiful as it is, I don't know if you read my post commenting on it, but I invite you to do it. Who is talking about the logical qubit with error correction? Everybody's talking about 10 to the 25 years. What people don't get is that the random circuit sampling was done with 105 physical qubits. The error-corrected qubit, the one logical qubit, is absolutely useless and irrelevant for anything in the next 10, 20 years at least. So whoever fantasized that that's a proof that there is a hope for fault tolerance doesn't understand technology at all. For reaching that moment, it took 20 years of work. One logical qubit that is in the threshold of fault tolerance that is not scalable because it's theoretically scalable. Now take one of these logical qubits and compose with another one and make a control node. You know what? It doesn't work in the same chip. In fact, IBM is a proof of that. The fact that they are going for the flamingo structure is because putting more qubits on a chip is trivial. Here, I have billions of qubits. The problem is that I cannot compute anything quantum mechanically. So to have qubits is trivial. And if you put more qubits on the same chip, it's trivial. IBM has 433 and 1,121. These chips are not useful. And they prefer to reduce the size of the chips and to compose them as a Lego architecture. So if you have one logical qubit as Willow, to have two on a similar chip is impossible today. So they will have to compose it. Prepare yourself. How many years will it take to compose two of those chips? So that's wonderful science, as I said. Science and a vision. But if you want to make quantum computers useful, you have to start by the hardware, and from the hardware is coming back. I was educated in a different school, perhaps, but my school, I follow the famous sentence of Asher Perez, who passed away, who wrote this book of quantum physics, right? And there was a comment. He was a very smart and funny guy, but he put. So the last message, I will stop here. It is. Quantum phenomena happen in the lamp, not in the Hilbert space. That's a dogma for me. Quantum phenomena happen in the lamp, not in the Hilbert space. I work from the lab to the algorithms. I don't work from the algorithms to the math. But you are free to do whatever you want.
All right. I think there's a few more questions, but unfortunately for now we reached the end of our time budget. Let's thank Professor Solano again for. So this was the last session for our Quantum W BW colloquium this year. We will be back on March 20th next year with a talk on design automation tools and software for quantum computing from Dr. Lukas Burkholz of the Technical University of Munich. Until then, thank you very much for joining. Happy holidays, and we are looking forward to seeing you again next year.